Okay, so today we're going to look at systems of equations problems. So we're going to take this idea of solving systems using substitution as well as solving them by elimination and as well as solving them by graphing calculator. And we're going to use it to solve some word problems today. So we're going to look at more real world situations. Here we go. So we're going to start today just with a quick review of solving by substitution and elimination. Then we'll try some word problems involving systems of equations. And then, of course, we'll get some practice. It shouldn't be too long of a lesson today. I'm looking in the printed note booklet. We're on page 11. It's only one page long. Well, 2 pages, I guess, page 11 and 12. But anyway, let's get going. So we're going to start with a solving by substitution question. I want you to recall that substitution required you to get one variable by itself and then substitute that equation into the other equation and then solve from there. So basically the key idea here is look at both of the equations you're given and think, okay, which equation that we have would it be easier to get one of our variables by itself? Or at least, perhaps more nicely put, which one would give us something a little simpler to put in? Between these two, I think this equation here on the right is a little bit simpler to get a variable by itself. And the one that I'm thinking about getting by itself would actually be the y. So to do that, I'm going to add y to both sides. And that's going to give me negative 6x plus 15 equals y. So now that I have this expression, negative 6x plus 15 equals y, I can just substitute what that y was equal to into this other equation over here. And what I mean by that is anytime that I see y in this other equation, I'm going to replace it with this minus 6x plus 15. So here we go. We got 4x squared minus y, so minus and then in brackets negative 6x plus 15. Those brackets are going to be really important. Minus 2x equals negative 7. Now, the reason that those brackets are really important is because of this minus sign out here. Because it was minus y, we have to take away negative 6x plus 15. Now, usually, I think that the easiest way of doing this is just to take this minus and think that you're double dipping it through these brackets here. So you're just going to take the minus and it's going to bounce here and it's going to bounce over here. So what that's going to give us is 4x squared, and then minus 6 is actually plus 6x. And then minus plus 15 is minus 15. And then, of course, we have this minus 2x over here equals negative 7. The next thing I'll do, this is technically a quadratic because we have an x squared right here. And since it's a quadratic, we like solving these by getting everything to one side, right? Because then we can solve it using the methods we've learned in the past for solving quadratic equations. First thing I'll notice is 6x and minus 2x. Those can combine to be plus 4x. And then I can add 7 to both sides to make this one side equal to 0. Long story short, it's going to give me 4x squared plus 6x minus 2x is plus 4x minus 15 plus 7, because you'd have to add 7 over. That's going to be minus 8, because negative 15 plus 7 is minus 8. And that equals 0. So now we have a quadratic equation here, and you're going to notice it's one of those adapted sum product rule questions. So you can use the adapted sum product rule that says you're going to have two numbers with a sum of 4 and a product of 4 times negative 8, which I think is negative 32. I'm sure you can go about doing it that way, but in all honesty, because all three of these numbers are divisible by 4, it might be easier for us to just kind of cheat the system here by factoring out a 4 first. So we'll have 4 times x squared plus 1x minus 2. Again, I just divided each of these terms by 4 and brought the 4 out. That equals 0. And now notice we just have a standard quadratic inside these brackets here. And that's a lot easier to factor. You don't have to use the weird factoring by grouping thing we had to do with the adapted sum product rule. So in other words, we're just going to look for two numbers with a sum of 1, because it's 1x here, and a product of negative 2. So two numbers with a sum of 1 and a product of negative 2, I believe that would be positive 2 and negative 1. So we have 4 times x plus 2 times x minus 1 equals 0. And then the two values of x that would make this true. So in other words, the values of x that would make this whole side equal to 0 would be x is equal to negative 2, because that would make this factor become 0, and that makes the whole thing equal to 0. Or it would be x equals positive 1, which would make this factor equal to 0. So there we are. There's our two solutions. But when you solve a system of equations, I want you to remember it's not enough just to have your x's. You also have to have your y's. And each of these are going to correspond with a different corresponding y value. Now, the good news is to solve for those y values, you just have to plug these x's into this other equation that we had here from the start, the one where we got y all by itself. So I'm going to start with -2. If I plug -2 into this, we're going to have y equals -6 times -2 plus 15, which I believe is 12 plus 15, which is 27. So y is equal to 27. And just because we have two solutions here, I often like just finishing this off, not just by boxing this, but also by writing it as a coordinate. One of our solutions here is the coordinate -2, that's your x from over here, and 27, which is your y, which we just found. And again, the reason I like doing that is this y equals 27 is tied to this x equals -2. When x equals -2, y equals positive 27. So we have to connect them, might as well write it as a coordinate. Now, same with this, x equals 1. I'm going to write it over here. Y equals -6 times 1 plus 15. That would be -6 plus 15. So that's going to be y is equal to 9. And again, you can box it, but it's really a good idea to make sure you write your answer with these kinds of questions as a coordinate, because that way we know that 1, x is equal to 1, goes with a y is equal to 9. So I'll write the coordinate as 1, 9. If you only had one solution for x, like if the only answer here was x equals -2 and you didn't have this other one here, then it's okay not to write it as a coordinate. But I think it's just a good habit to get into, to write your answers as a coordinate, because then you know which x goes with which y. So to summarize what I just did there, because I feel like I kind of just spat it out real quick, to solve by substitution, you need to get one of your variables all by itself. It usually doesn't matter if it's your x or your y. I chose to get y by itself here because it was a lot easier to get y by itself here. And I used this right equation rather than the left one, just because it looked like a simpler equation to work with. Once you have something that variable is equal to, so in this case, it was y equals -6x plus 15, substitute that into the other equation for every single time you saw that isolated variable, and then just solve from there. Oftentimes, it's going to rely on our understanding of quadratics, as we just saw. Sometimes you get lucky. Sometimes it's just a linear equation. This time, not so much. Anyway, moving on. Next one, solving by elimination. I'm going to let you know my bias here. I hate these kinds of questions. I really don't like solving by elimination, but some people do, so whatever floats your boat. Plus, we have to learn both ways, so whatever. Anyway, to solve by elimination, line up your variables, multiply an entire equation by a number to make the variable match if necessary, and then add or subtract them together and then solve from there. There always just seems to be more steps with these. That's why I don't really prefer them. Anyway, the key first step here, line up your variables. Often relies on us rearranging some of our equations. I think if we look at this right-hand equation, maybe we should bring everything to one side so that it's like this one where it's equal to 0. And then we'll also rearrange it so that we have x squareds, y's, x's, numbers equal, and then 0. Long story short, what I'm trying to say is take this right-hand equation and write it using x squareds first, so -2x squared. Then we'll write our y's. Well, we have minus y here, so I'll just move it up here because why not? Minus y. Then we'll write our x's. Well, we have -16x, so that's fine. And then we have our number. Well, 35 is over here. Let's minus 35 from both sides. That'll make it -35 here. So good. And then we'll have an equal sign, and then that equals 0 because we moved the 35 over. Then you take this equation and you line it up with this other one. So line it up directly, -2x squared minus y minus 16x minus 35 equals 0. Now, it's up to you whether or not you want to add or subtract these together. Sometimes you have to multiply one of your equations by something to make your variables match. But if you actually notice here, all of our variables have matching coefficients to some extent. If we were to add these two equations together, so if we were to go 2x squared plus -2x squared and all that, if you were to add these together, you would actually cancel out all your x's and you would just double down on your y's. That's fine. If you wanted to subtract these equations, so 2x squared minus -2x squared, you'll keep all your x's, but you'll actually eliminate your y's. So you'll end up having a quadratic equation to solve. You can do it either way. You can cancel out your x's here, or you can cancel out your y's. Personally, I think it would be way easier if we added these together and cancels out all of our x's so that we're just left with a y statement. Here, let me show you what I mean. -y plus -y is actually -2y. All of these x's, of course, cancel because 2x squared plus -2x squared is gone. 16x plus -16x, those are gone. But then we have plus 29 plus -35 which I believe is actually -6. So we have minus 2y minus 6 equals 0 plus 0 is still 0. And then that becomes actually really easy to solve. It's just -2y minus 6. That's a linear equation. Let's just add 6 to both sides. So -2y equals 6. And then divide by -2. So y is equal to -3. That was actually really, really nice. It's usually doesn't work out quite so well. Anyway, so now that we know y is equal to -3, just take that and you can throw it into either one of your original equations and solve for x. Personally, I think maybe we should use this right-hand equation. It really doesn't matter too much, but whatever. I'll plug it into the original one instead of this one where we rearranged it. So it's going to be -2x squared minus 16x, and then minus y, so minus -3 equals 35. You know what? Maybe I will actually bring everything over to one side because now it seems like we have a quadratic here. This is going to be -2x squared minus 16x minus -3 is plus 3. Maybe I'll just go here. That becomes plus 3. We can minus 35 over to make it -32 equals 0. Okay, so this is a quadratic. We got to solve this one. It's one of those adapted sum product rule ones because we have a number in front of our x squared. So you could look for two numbers with a sum of -16 and a product of -2 times -32, which is 64. I'm sure you could make that work, but I also see something else I can do here to make my life easier. I could factor out a -2 from all of these to turn it into a normal sum product rule question. So since -2 comes out of all of this, this will become -2 times x squared plus 8x, because I took a -2 out of there, and then plus 16 equals 0. So again, what I did was I just factored out a -2 from all of this. This leaves me with a normal sum product rule question. So I don't have to fuss with the whole adapted sum product rule thing where you factoring by grouping. That's where you put brackets around the first two, brackets on the last two. It's a whole ton of work. Save myself the trouble of doing that there. Looking at this just normal sum product rule question, we're looking for two numbers with a sum of 8 and a product of 16. Well, that would be 4 and 4. So this just becomes -2 times x plus 4 times x plus 4 equals 0. That means this is going to have a solution where x is equal to -4. And then this one's also where x is equal to -4. So I'm not going to write it a second time. Bingo, bango, bongo. We got it right there. X is equal to -4. And that is your only solution on this. So you don't have to write it using a coordinate like we did in the last one. But you know what, just for fun, let's do it anyway. So our coordinate answer here is going to be -4, that's your x, and -3, which is your y. And that is your only solution here. That is the only value or only coordinate that'll be the same on both of these graphs. Perfect, we got it. Anyway, moving on. All right, so here's an actual word problem that we're going to deal with. These are a lot more common than the other questions because, of course, solving a context is actually what's important in all this. Skeet shooting requires a shooter to hit a projectile while in flight. The target is launched on a path defined by h of t, so height as a function of time, equals -2t squared plus 20t, where h of t is the height of the projectile in meters and t is the time of the projectile in seconds. And the gun is shot along the line h of t equals 14t. So I guess that means that's the path of the bullet. It's kind of weird that saying it's the gun is shot. That'd be the path of the bullet, right? The projectile is this guy, and then the bullet follows a linear line of this. All right, so after how many seconds does the shooter hit the target? Solve algebraically. So when it says solve algebraically, and this is a system of equations, you can either use solving by substitution or solving by elimination. Again, it's whatever floats your boat. Personally, I prefer to solve by substitution. So I'm going to use substitution on this one. That means I need to just get one of my variables all by itself. Don't worry about the fact that this is a function, h of t. If it makes you a little bit more comfortable, just call it h, right? Height equals -2t squared plus 20t, and height equals 14t. Maybe that makes things a little easier for you. Certainly makes things easier for me. So if I'm solving by substitution, that means you just need to get one of your variables all by itself. And if you actually look, both of these formulas already have a variable all by itself. Your height is already by itself. So what I'll do is I'll substitute this value of the height into the other formula up here. So I'll say 14t equals -2t squared plus 20t. From here, we need to solve this, of course, because it's a quadratic, we need to solve this by getting everything to one side. So I'm going to minus 14t from both sides, and that's going to give me 0 equals negative 2t squared plus 6t. Now, you could try using the adapted sum product rule on this one, but personally, it'd be easier just to factor it like the old-fashioned way. We can take out a negative 2t from both of these, so this is going to be 0 equals negative 2t times, I guess this would just be t minus 3. And then, of course, our solutions, because it's just something times something, our solutions are going to be t is equal to 0 and t is equal to 3. So let's analyze these answers here for a second. What this means is the projectile, which is this guy right here, negative 2t squared plus 20t, is going to be equal to the bullet, which is the 14t, at a time of 0 and a time of 3. Well, if you think about a time of 0, that's like literally the very moment that that projectile is shot out. And that doesn't really make any sense. The very moment that the projectile is launched, it shouldn't be the time at which the projectile from the gun or the bullet from the gun is actually meeting the target, right? That doesn't make any sense. So just contextually, we can cross out t is equal to 0 because that's a nonsense answer. The better answer here would be t equals 3. So at exactly 3 seconds, the bullet from the gun is going to strike the launched projectile. So I think 3 seconds is really the only one that makes logical sense. Next part of the question, how high is the projectile when it's hit? Well, you had to solve the first question, have that first. We knew t is equal to 3. We're looking for the projectile. So I guess that would be this guy, although really should give you the same answer one way or another. Anyway, you can just throw 3 into that formula. So h of t equals negative 2, 3 squared plus 20 times 3. That is going to be negative 2 times 9. That's negative 18. Plus 20 times 3 is 60. That's going to equal negative 18 plus 60. That is 42. And I suppose really we should answer it with units. That's 42 meters. So the projectile is 42 meters in the air once it is hit. Whew. All right. Hopefully this is making sense. I know I'm kind of flying through this. We're actually already almost like 17, almost 18 minutes actually into this video. So I apologize. It's going longer than I thought. But hey, you know what? We're having a good time. Or maybe I'm having a good time. I don't know about you guys. Anyway. The 2,015 meter tall Mount Asgard in Nunavut was featured in the James Bond movie The Spy Who Loved Me. In the movie, Bond skis off a mountain and then deploys a parachute. The function h of t equals negative 4.9 t squared plus 2,015 represents his height before deploying a parachute. The function h of t equals negative 10.5 t plus 980 represents his height after deploying a parachute. How many seconds did he wait to open the parachute, and at what height was it deployed? All right, here's the deal on this one, guys. I'll kind of help you out with this. Nowhere in this question does it say that you have to solve this algebraically. Oh yeah, so that means you can use your graphing calculator to your heart's content. Basically what this means in this question is that since he's jumping off the mountain at a height of 2015, because that's how high the mountain is, right? Hence, when t is 0, you have 2015 as his height. He's jumping off the mountain and he's following this path. This is a quadratic. Matter of fact, it's an inverted quadratic because there's a negative leading coefficient. So his initial path that he follows is going to look something like this, right? It's a free fall, right? So if you jumped off a mountain, yeah, you look kind of like this, right? It's free fall, right? However, eventually he deploys his parachute, and that function follows this linear line. It's a linear equation because there's no t squared, it's just t, right? So this is a mx plus b kind of question. It's a straight line. And that's going to represent, of course, his height after deploying a parachute. And that line's probably going to look something like this, right? So if you were to graph this in your calculator, it is going to look something along the lines of this. What we're looking for is this point right here, the point where he deployed his parachute. And I'll just change color real quick just to really highlight what's going on here. In blue, this is going to represent his actual path. He's fallen off the mountain, free fall, free fall, free fall, no parachute, and then whoosh, parachute. And he's just gliding. It's not a very good straight line, but you get the idea. Just gliding down. Nice, straight line. Okay, we want to find that intersection point. Let me erase this just because we're going to need the room. What I would do if I were you is I would put this equation over here in your y1, and this equation right here in your y2. But we're going to need to change our window here, right? Because our window needs to encapsulate both of these. From that little thing I drew just a second ago, I'll just really roughly redraw it. Remember, the mountain that he's jumping off is 2,015 meters tall. This is going to represent your y max. Okay, so your y max needs to be at very least 2,015. So of course, that's what you're gonna have to change there. Your y min, you might as well leave it at -10 just so you have a little bit of wiggle room. -10, of course, is the standard y min. Your x, however, we really don't care about any negative x's, but why not just leave it at -10 just because, you know what, why not? As for your x max, we have to kind of guess a little bit until we get it. I want you to think critically about this. And you don't have to blurt it out or anything. I'll tell you what I think in just a second. Like, why would you blurt it out at your screen while you're watching this? What am I even talking about? I want you to think logically. X represents the time after he's jumped off the mountain. If you're jumping off a mountain, roughly how many seconds do you think it would likely take, let's say, for you even to hit the ground? I would be surprised if it was anything more than 30 seconds. So you know what? I think a good X max here might be 30. I might be wrong on this one. Let's see. Hint, hint, wink, wink, nudge, nudge. I'm not wrong, but hey, anyway. So again, you'll want to break out your graphing calculator, give this one a try, throw it into y1, throw it into y2, and then we have to find the intersection point. But you know what? We can do better than just me telling you that. Ba-bam. Look at that. I got a digital Texas Instruments right there. You didn't even know I could do that. I'm going to do it for you. Anyway, let's turn this thing on. There we go. Ready to roll. So y1, I'm going to throw my -4.9 t squared. Well, instead of t, you have to put x in your calculator just because that's how they work. So x squared plus 2015. There we go. Then in y2, I'll do my -10.5 t, so just x, and then plus 980. And then before I even try graph, well, you know what? Let's press graph just for fun. Nothing shows up at all. Not a big surprise. We got to change our window here. X min, leave it at -10. That's -10 seconds. Who cares? X max, like I said, probably take 30 seconds for him to hit the ground at the very most. We'll find out. X scale, I'll leave that at 1. Remember, that's just like little ticks that show up. No, you know what? I'll change it to 5 just for fun. That's the ticks that show up along your x-axis. Y min, that's of course his height, -10 meters. So 10 meters underground. Why not? And just leave it there. Y max, we're gonna have to really ramp that up. Remember, 2015 should be the absolute lowest Y max you set it to. I want to give myself some wiggle room. How about I say 2100? That'll give you, yeah, a good amount of wiggle room. As for my Y scale, so how many or how far apart my little lines are on my Y axis, I'm going to say 100. Because you know what? Why not? Now I'll press graph. Let's see what happens now. Ooh, there it is. So that's him falling off the mountain free fall. This line represents after the parachute. This segment of the line right here on the left is just pointless. That's not actually what's happening. He's deploying the parachute as soon as these intersect. And the same can be said about the rest of this quadratic down here. That's not actually happening. Only this curve right here, that's his free fall after jumping off the mountain. And this straight line here, those are the only parts that are actually happening. We want to find how many seconds he waited before he deployed the parachute. So we need to find this intersection right here. To do that, press second and then trace. Go down to where it says intersect. Press enter. This little blip thing shows up. You want to move it as close as you possibly can to that intersection point. I think that is probably a pretty good guess. I'm going to press enter. It says a second curve. That's pretty good. I'll press enter again. And then a guess. That's pretty good. Enter again. And what do you know? We got 15.64 and Y is 815.7. So you know what? Just to round to the nearest 10th, because I don't think I actually put in this question how much to round to. We'll just round to the nearest 10th. Let's write that down back over here. Oops, oh, didn't mean to go forward. Sorry, guys. We will say the amount of seconds he waited to deploy the parachute. So T is equal to 15.6 seconds. There we go. And at what height was it deployed? So I'll say H equals 815.7 meters. See, that wasn't too bad, right? In these kinds of questions, again, it's always just finding the intersection, and using your graphing calculator here was a lifesaver. Imagine if you had to do this using substitution. I mean, you could have done it. It would have pretty much relied on using the quadratic formula, but you know what? Let's not do that. Let's do this one instead. All right, so a ball is hit in a baseball game and models the path that. The outfielder jumps to catch the ball, and her path is modeled by the equation that. Let H be the height of the ball in meters above the ground, and X by the distance, it should be the distance the ball has traveled from home plate. Solve this system of equations and interpret the meaning of the results. So when it says solve this system of equations, that just means find where these two equations are equal to each other. Once again, it doesn't say solve algebraically. Wahaha, we can actually solve this using a graphing calculator. So boom, I'm going to bring this back. Let's go quit all this, clear all our old stuff out of here. Just throw those two equations in your graphing calculator. Like, why not, right? So let's just send that first one as being negative 0.1x plus 2x. That's the path of the ball. And then the path of that outfielder, she's got negative x squared plus 39x minus 378. It's quite a formula. Before, well, you know what? I always say before. We'll always just graph first. Graphing this using my old graph from the James Bond one. Clearly, we're not getting anything. We have to change our window here. So if we're thinking about a window in this case, remember that h represents the height of the ball above ground in meters, and x is the distance the ball has traveled from home plate. It's kind of hard to say in terms of a baseball diamond if you're not too familiar with that, because x again is a distance this time. It's not a time. So what I would say, maybe let's just leave our x min as negative 10. Maybe our x max, let's leave it as 30 for now as well. 30 meters seems to be a pretty good distance for a baseball diamond. I don't actually know how big they are either, but just a good starting point. For a y min, negative 10 meters, so 10 meters below ground, that's probably a bit low, but you know what, we'll leave it there as well. As for a y max, this is the height of the ball above ground. We definitely don't need 2,100 meters like we had before. I'm going to set it just to 10 meters for now, and then I'll just set my scale back to 1, because why not? Let's see if this graph helps any. There's that first equation. That's the path of the ball, probably. Did I put this in correctly? That doesn't even look right at all. Let's see here. Go back. Oh, I didn't set it right. You guys probably already screaming, oh, you screwed up. You know what? It's whatever. People make mistakes. There we go. That's got to be negative 0.1 x squared plus 2x. My apologies, guys. Anyway, moving on. Let's see this again. Whoosh. Okay, that's the path of the ball. That's the path of the outfielder. There we are. So now we have an intersection point. You can ignore everything that's below your x-axis here, because that's stuff that happens below ground. That's nonsense. That doesn't actually happen. So we're looking for the one intersection point, which seems to be right here. So if we go second trace intersect, and then I use my arrows to kind of move this over. There we go. Too far. There we go. Enter, enter, enter. And we are getting 18.96 and 1.96. And you know what? I won't round to the nearest tenth this time. I'll round to the nearest hundredth. So again, we have x. Hold on. There we go. X equals 18.96 meters. And y, or in other words, h in this case, h equals 1.96 meters. So that right there is the solution. That's our intersection point. You could have listed that as a coordinate if you wanted to. It's whatever, like however you want to communicate it. But it does say interpret the meaning of the results. Well, x, like we said in the question, is the distance from home plate, and h is the height of the ball. So what this means is at a distance of 18.96 meters from home plate, she caught the ball at a height of 1.96 meters. Okay, every now and then we'll throw like a word interpretation in as well. That's just basically getting you to look back at the question and say, hey, what did I just do? It's easy enough just to like plug both those equations in your calculator and say, oh, that's where they meet. It's another thing altogether to say, hey, what does that actually mean? Right? So in other words, she was 18.96 meters from home plate, and she caught the ball at a height of 1.96 meters. So she might have had to jump a little bit, or at least put her hand way up in the air. Well, I guess 1.96 meters isn't all that high. That's like 6.5 feet, I think. Anyway, whatever, we're done. I'm gonna stop yapping your head off here. So, wow, I lied to you at the beginning of the lesson. I was like, hey, it's only one page double-sided. This should be short and easy. And you guys would have actually seen the length of the video before we even started. So you went, oh boy, what is he doing? Anyway, so practice. Here's the questions, they're on the screen. Really, really essential, especially these second set of questions right here, because these are the word problem ones, I believe. Make sure you're giving these a try. Of course, practice is essential. You can't just watch this and expect to know what you're doing. But hey, this is it for chapter 8. We're done chapter 8 already. Yay! Tomorrow we'll be in chapter 9, which is in the exact same booklet because it's like basically the same thing-ish. Chapter 9's got like a little bit more graph stuff that we do when we deal with inequalities instead of equations, but I will leave that there. Anyway, you know where to reach me if you need any help. I am on Zoom. Best of luck.